All right. So, like I said, section 24, right? There's actually a lot of stuff that we're talking about in this section that will lead right into mod 3. We're kind of getting into the points of when we start doing more predictive modeling. We've been kind of talking about for mod 2, a lot of like analysis um, of like the data itself. And what this will lead to, like, for example, we just started talking about from linear regression, we talked into naive Bayes. And naive Bayes is really like our first like classically thought of as a machine learning algorithm. So mod 3 is basically all machine learning, and then even mod 4, we go into more advanced machine learning techniques and stuff like that. And these are very powerful techniques and everything that you can do, but it's also really important to understand what the algorithm is doing, because a lot of times the way ML models work, you kind of give it the data and you're not really interacting with it once you give that data. So you have to understand, what am I giving it? What do I expect the algorithm to do with it? And how are the ways I can test the algorithm and making sure that it's training and basically creating a good prediction. And how do you test against that? Especially, like we said, our data might not be perfect. You're saying, okay, like how do we know it's doing a good job? And so we'll talk a little bit about that today. Okay, no problem. Sorry, well, but what was I saying now? This techniques the stuff we're going to talk about today, especially we'll learn about what's it called, bias and variance. Those things will be particularly useful when we start talking about our machine learning algorithms for next module. Okay. So, any questions so far? No. Okay. Cool. All right. So I'll go ahead and start sharing my screen. And hey, Assad, it's nice for you to drop in. Okay. Okay, so you guys should be able to see my screen. I'm actually gonna make this a little bit wider, if you guys agree with that. Okay. Just thumbs up, you can see my screen, just double checking. Cool, awesome. All right, so we're gonna kind of start off where the curriculum kind of goes through. Basically, the curriculum starts off with showing linear regression. We start off with linear regression. That's what we've kind of known since last module, right? The end of last module. And we're saying, how can we improve it? So a lot of these pictures are just from the curriculum. So that's why I've used the same ones. That way, when you guys go through the curriculum, you also recognize them, okay? But the main thing is we'll look at improving linear regression. This is our first start. So we have something called interactions. And it's actually kind of funny, like even the curriculum kind of makes a little joke about it. It's like, well, this seems really easy. Is that an interaction is just when variables are interacting to cause an effect on another variable, but it's not the sum of their parts. So you can kind of think about this as that, like when we talk about like an interaction in this way, and they'll specify that it's not an additive interaction, which basically means that like if you do A and you do B, then the effects in A and B get added up together. But you can see something in the interaction where it's not additive, where like A makes it go up, like let's say your target go up. A makes your target go up, B makes your target go up, but then A and B together might make your target go down. So I'm trying to think of a good example of this, but like you can imagine almost like buckets, right? It's like, like they're interacting with each other. Forget the buckets. But you can kind of think of this different ways. So there's an example that the curriculum gave that I thought was a good one, is that they were saying like, okay, let's imagine this. I don't know if it's a real study, but they said, let's pretend this is a study here where you have diets A, B, and C, right? And they all have different kind of like attributes of what this diet is. And you want to see what's the best diet for weight loss, right? So your weight change. And they found basically for the USA, so they tested in countries, the USA, UK, and then New Zealand. So if you look at the USA, basically diet C was the best. And then we have diet, what's it called? Diet A and then diet B, right? So it goes C, A, B, right? And we see the same thing actually in the UK. Maybe not much of a change, but we can see that one's clearly better. But when we look at something like, in this case, New Zealand, we actually see that A ends up being better and C actually ends up being the same as B. And so this is what basically they're pointing out, saying this is a conflicting factor or a confounding factor. Sometimes you'll hear people talk about like conflicting variables too. It's kind of like the same idea, but the main idea is that there's something adding up together in this way. And the confounding factor in this case is the country, is that something about New Zealand basically makes B and C seem the same. Now, this is a really simple example, but we can get very complicated with like more continuous variables. But the point is that there is something different about this factor of what country it is that affects what the weight change in diet. Make sense? Okay. This is actually really important too, because this kind of goes into when you look at your variables or when you're looking at your analysis, you don't necessarily, let's see here, like if we pulled everyone together, like USA, UK, and New Zealand all together and didn't specify that there's someone from either USA, UK, and New Zealand, we can actually get a different effect, right? Maybe New Zealand, let's just pretend there's a lot more New Zealanders in the population of the sample, or at least in the sample. And so they might overpower the effect that we see in the USA and UK. And it just turns out that New Zealand had a specific confounding factor, okay? So that's kind of the idea when we talk about interactions. So there's a couple more examples I can kind of go through. I want to show you guys. So this one right here is an example of a slight interaction, mostly additive. So this is from the curriculum. If you guys remember in the curriculum, I think it's like almost like four sections ago, they started talking about, what was it? They used the car data with like it might even be longer than that. It might have been module 1, but they had some car data and they had something like horsepower, the origin of the car, how old the car was, and they wanted to see their target was miles per gallon. It was just an example they showed. So this is where this data is coming from. And so basically they're saying, okay, let's see if there's any interaction factor or there's any interactions, confounding factors. And so in this case, they said, okay, let's just go ahead and take the horsepower. And then our targets are MPG right on the side here, okay? We say, let's go look at separately, basically, let's try to make a regression line just for the origin, origin equals 1, origin equals 2, origin equals 3, okay? So those parts, what's it called? We're looking at those separately. And you can see the regression lines, like they kind of drew this out, you know, on the plot. You can see that they're pretty much the same, like they're the same slope, like they're slightly moved up, which is actually what we'd expect. Because if you remember back when we do linear regression for multiple, right? What do we do if we had a category? Does anyone remember?
One hot encoding.
One hot encoding, perfect, right? When we do one hot encoding, basically we take each of these variables or each of these, of the feature, we separate those out into their own features, right? We say, oh, if you're origin 1, you know, you're true or false or whatever, right? And what that effectively does, it makes a variable. So instead of having, let's say, this variable origin, right, which could be 1, 2, or 3, instead what we share it into 3 different variables where we have, x, I'll put or 1, x, or 2, x, or 3, right? And when we add this up into our linear regression looked like y equals, and then we have like our bias term, okay, w0, and then we have something like w1 times x1, right? I'll just put like x1 for the origin 1. I know we'd have something like plus w2 x2, and then I'm running out of room here, but you guys get the point, hopefully. w3 x3, right? And because we one hot encoded, this is either 0 or 1, right? It's one of those two, right? So if this is 1, these two will be 0, right? So what that effectively does is says, okay, basically if this is 1 right here, it'll just have some basis term. These will be 0, and then the rest of the linear equation. So essentially what it does, it just boosts it up or down, the whole thing. And that's what we mean by additive, right? It's like, oh, if you're just slightly up, slightly down. And that's actually what we see here. So for example, is that maybe the base one, for example, origin 1, is that this is the linear regression, and then we slightly boost it up if it's origin 2, right? It has a different factor. It basically has this extra W2 term, would move it up to this red line. And then of course W3, it looks like if we had W3, looks like W3 is even bigger. So W3 kind of just effectively moves it up. Essentially adds up to this W0 term. Does that make sense? Okay, so, and you can see that's what we look like. It looks pretty parabolic. You can see it's not quite there, and the curriculum actually shows this in mathematical terms. You can do this calculation really quickly and see that it's not quite the same slope, which of course, if they're not the same slope, they'll eventually intercept. But it's like, oh, okay, like it's probably not that bad. Turns out though, if you actually try to do the interaction, the curriculum shows that you actually get a slightly better R squared value. So it turns out even though they're slightly additive, like they look more additive than our confounding factors, you do actually benefit by saying, well, okay, let's go ahead and try to treat these as if they're interacting. Okay, so that's an example of just one that's like maybe a slight interaction, but mostly additive, but it still benefits from actually accounting for that interaction. Okay, and this one right here is definitely not additive, right? You can't simply just like move that blue line upwards, you know, like just kind of like moving it up or down to fit with that red line. You have to twist that blue line to fit with the red, which means it's a different slope. And you see in this case, the categories are still horsepower, but it's either older or younger cars. And you can see basically, even though as the horsepower increases, we see MPG goes down, but it goes for, it looks like younger cars, it looks like it significantly goes down as we get to higher horsepower. If we get into a lower horsepower, we actually see that younger cars do better than older cars, okay? So this is something where it's like, okay, there's clearly an interaction, and this interaction, the confounding factor is between older cars, younger cars, basically the age of the cars, and the horsepower, okay? So that's what's going on here. So the way we can treat this and actually do interactions, so the code in the curriculum that actually shows us in the code, is that if we had those interactions, I'm gonna use a better color than that green, because green was hard to see. But like if we had this linear regression right here, and let's say this is one hot encoded, this is like, oops. This is like W, come on guy, there we go. This is like W older cards, and I'll put W just Y, okay? What we can't, like those are the coefficients, right? And then it'd be multiplied by their X old, X young, okay? And then we would add up all these parts, right, for the whole linear regression. Basically what you say is like, okay, let me add a different term, and this term instead is our interacting factor. And our interacting factor will look something like some new coefficient, I'll just call it WOY. So some coefficient that's different from this one and that one, okay? And we multiply it by the factor XY and the factor of X old, okay? And basically that allows us to tie those two together. So that way there is some kind of interaction between the two. And this is basically when we multiply WO, we have this new factor now that we can account for and we can trade on top of, right? And so that's actually how you kind of try to solve this like interaction factor. Of course, now it's kind of like you have to say, okay, like how do I actually find these factors? And that's actually why we get into machine learning, but like we'll get more into that later. But the main part is that we can actually account for these interacting factors. So these are things, for example, if you have many, many variables, you can imagine, you know, if you have 20 variables, right, you're going to have to look at, you know, like factor 1 and factor 2, factor 1 and factor 3, factor 1 and factor 4, and then do the same thing for factor 2, factor 3, factor 2, factor 4. Like you can see there's a lot of interaction that you could like end up playing with, and it can be very, very difficult. So this is one of those things where it's like, okay, this can be really like a lot of work kind of stuff, and that's why we do new techniques.
Okay. Quick question, and if this is like too out of context, then just tell me. But is this sort of like the same effect that you would see if you were doing like, let's say, a pair plot for regression, but you used hue and put in a categorical variable for hue? Is that sort of, would that give you the same thing?
Yeah, you'd get this similar plot, just not with the lines, I think. I think you would just...
No, well, I'm asking because you do definitely get the lines.
Yeah, I think you would be able to get this. I think the code in this case, they specifically took these features, but in a pair plot, you would at the very least get the scatter plot. And I think, yeah, I think you're right. You do get the regression lines.
Yeah, I'm asking because there's one in my,
yeah, and that's what you could do. You could do... what's it called? You could do a pair plot and see those interactions. And again, that's why it's like visually, it's a lot easier to look at, like us visually, we can see that very quickly. Like I can look at this and say, oh, that's close, but it's not quite, right? It's not quite not interacting at all. And that's where, again, like I always say, it's like you as a human, like visually be able to see something can help you tell a hunch. It's not going to tell you everything, but it can give you like, okay, maybe I should look about this a little closer. Versus like the curriculum just outputs the numbers, and it's like, the numbers are like 27, 28, and like 25. Or I think it's 25, there's like 26 or something. And they're relatively close together, but it's hard to visualize, like, what is a slope of 28? At least for me, like, I'm just like, I don't know exactly what that would look like immediately and say, well, okay, what degree of slope is that? You know, are they close, or is like that not close enough? So those are the kind of things that you can do visually very quickly. And that's why I like showing this part too. Yeah, cool. But yeah, you could do pair plots. That would be one way to check it out. Okay, so this kind of leads us into another way we can improve, what's it called? We can improve our linear regressions. So I actually kind of hinted about this before, is that we can kind of do transformations on our data to make more general linear regressions, and they're no longer linear regressions, they're really polynomial regressions, right? So you can actually see that we actually did a polynomial regression here to do the interaction. We just did, let's say, like, you know, X old and X young multiplied together. That's no longer linear, right? That's now they're interacting with each other. We have basically essentially a degree to, even though it's two different variables. But here we can actually use something where we look at each individual variable. So kind of going back a little bit is that if we think back on our multiple linear regression, this is, I kind of wrote this down a little, but this is the equation, right, of our multiple linear regression. If we had capital N features, right, then we would have, you know, this whole equation, W0 just being a coefficient, you know, we'd have to figure out what those coefficients are, W1 being a coefficient, X1 being a feature, and then all the way through Wn, Xn, right? You'll see a lot of this notation. That's why I kind of wrote it alternatively. So you might sometimes see this written out, but a lot of like strictly math stuff, they'll tend to write the summation form because it's more condensed and stuff like that. So just be aware, especially as we go into Mod 3, you're going to see summations all over the place with indexes. So I would suggest is that if you especially feel not certain about summations, definitely take that time to really understand what's going on here. But I'll kind of walk you guys through it real quickly. Is that n equals 0 here? That's basically saying the variable underneath here is saying, hey, this variable is going to be one that changes. So we'll have W0, X0. Okay, and those are just the indexes, saying that these are specific ones. I shouldn't really put X0 here. That might have been kind of a bad thing. But you can think of X0 as being equal to 1, right? You notice that if I just set this to 1 right here, that'd be like X0. This is kind of the notation sometimes. I could have also put like N1 here. And then this cop letter right here is just saying how many things it goes through, the number of things. So I could put like 10, and that'd be 10 features. Okay, cool. Just wanted to show you guys that because that's how it's written out. So again, one thing I want to ask, why do we say this is linear? Because this is clearly not a line, but why can we call it linear? Or why do we call it linear regression based off this equation? I kind of want you guys to think about this, because when you start seeing this more and more, you'll start recognizing linear relationships not. Yes, anyone got an idea why we call this linear? Okay. I'll give you guys a little hint. What does it look like? What kind of equation is this one right here? This y equals 0, W0 plus W1 times X1.
Yeah, it's like y equals mx plus b, I guess.
Yeah, it's y equals mx plus b. It's a line. It's the equation for a line. The only thing that can change is x1. Now, we're just adding the next part, w2 here, right, the x2. But if you think you covered everything else up except for w2, x2, that's just another line, right? Basically, you can think of it just adding up a bunch of lines in different dimensions, right? In dimensions, I mean like x1, x2, x3, like those different dimensions. So that's why we call it linear equation. There's just a bunch of lines being added together, essentially. Okay, so we could always take a slice and always see a line, right? We don't have to worry about that. So we can actually make it more complex by doing polynomial regressions. So the first thing you can do is like, okay, let's check out this data set. Now, first things first, can you draw a linear regression line through this and accurately predict it? Is there any line we can draw through this data that would fit this data well?
Nice moon.
Yeah, it looks like a moon, right? There's no way, like no matter what line I draw, it's just never going, it can get close, but it'll never completely describe this data as well as some other shape, like Paul had mentioned, like maybe like a moon or something like that. So like maybe I need something like moon shape like that. And that's actually the whole point. It's like, okay, like we can't draw, and this is what we talked about before in Mod 1, is you can't make a linear regression if your data is not linear, right? And so we can actually say, well, okay, what if we take the concepts of linear regression and instead kind of modify it so we can allow polynomials, okay? And a polynomial, if you guys recall, is just basically something to the power, right? So for example, a simple polynomial, I mean, technically this is a polynomial, you know, x, but we could do x squared, that's a polynomial, plus x, that's a polynomial, you know, this would be a polynomial as well. Basically, it's just, you know, a degree. And we talk about the degree of a polynomial. Does anyone remember what the degree of this polynomial would be? Okay, yeah, so our degree is the highest power of the polynomial. So in this case, it's a degree of 3. Okay, if I had plus x4 here, that degree would be polynomial 4, or a polynomial degree of 4. Okay, if I only had y equals x, what would be the degree of this this one? 1. Good. I cited Jonathan putting up the 1. Good. Yeah, and of course, last one. Not really. Okay, we'll talk about it. What's the polynomial degree of this one? 0. Okay, good, Joe. Yeah. Yeah, so it's 0, because the reason why we can say that's because x to the power of 0 is just 1. So we can just say, oh, that's a degree polynomial. So that way you can kind of know when we talk about degrees. It's just what the highest order, like what the highest one is, okay? So we can do right here is we can say, oh, this looks more like it looks more like a moon, a parabola, like something kind of that shape, right? And so we can say, okay, we can imagine instead of doing like with our linear regression, in this case, we just have temperature. We don't have multiple variables, but cool. It's like a simple, if you imagine, if we tried making a line on here, like I drew a line like this, we would have something like, you know, y equals, you know, I don't know, 3 plus 0.2 x. That clearly won't work, but that's the whole point. You would have some value like this, right? Or if I wrote it in like more general form, w0 plus w1 x, and x being the temperature. So there's only one variable, but I'll put one w1. So that would be like our regression line, right? So what we can do is like, well, okay, let's make it more complicated. Let's allow multiple polynomials. So this one, for example, probably looks closer to a parabola. So does anyone know what would be a general parabola formula? You want to take a shot?
X squared.
Okay, x squared, good. We need that part. So obviously though, we can like scale the x squared, right? We can make it smaller and bigger. So we'd have something like, you know, some number in front of it. So I'm actually gonna do this part. So we had something like, you know, the letter a, x squared. Okay. And obviously, if you kind of remember back from calculus or algebra 2 or whatever it was, you can adjust that parabola up and down, right? So we can add a constant term, right? So let's just call that plus b with no x's in there. And the last thing we can actually add is another x. Okay. Now, usually you wouldn't draw this out. Like, I think if you remember back, like way back, probably in high school, you know, when you learned about like algebra 2, like, you know, graphing and stuff like that, you might have seen something like x minus b plus, you know, like, I don't know, I think it was like k or something, squared like this. Okay. And basically it ends up being something along the lines of like ax and then times the constant. Basically you have an x squared term, an x term, and just a constant term. So like some constant, and be like this. Okay. So the point is that you can have up to x squared and then everything else underneath that. Okay. And that's a general quadratic equation or parabola, right? So we can do that. So this this right here is a way to take only one variable. Note this is just x, not x1, not x2. It's just x. And we can say, okay, there's this constant beta. I just used a different letter than w, but it doesn't really matter what the letter is. In this case, this is what the curriculum uses, so I'm sticking with it. But this beta right here is just that value multiplied by that polynomial term. So there's just, for example, this is just x to the power of 1, x to the power of 2, and then all the way through x to the power of capital N, right? So we can see we can make it very, very large. We could like have like up to like 10, 20, 30 degrees. We probably don't usually do that just because you can imagine, this is just for one variable. Imagine having 30 different terms just for that one variable. That already adds, you can already see computationally why that might be an issue. Is that it just would take a long time, especially if you have multiple terms. So we can actually create it with multiple terms as well. But kind of quickly showing you is that this is, for example, an x squared right here. But this right here can be done with, like this might be something like a polynomial degree of like 10, where we have these extra little curves and stuff like that. Basically, you can think of like almost every time you see like an inflection or point up, you can think of that almost being like another degree of the polynomial. So you can see that there's quite a lot of extra bumps here and stuff, but we could actually, we can actually do this. We can decide, okay, I want to try a polynomial degree of 10. So it's up to you, right? And of course, if we were talking about multiple variables, that's when it gets more complicated, but you can think like doing this whole process up here, doing this whole process right here, okay? But doing this whole thing for each individual feature. So you can think of doing it for this one, doing it for this one, doing it for this one. And I was using notation here where basically you can see each one's a sum, and I'm basically have to sum over all those sums. And I gave each a little subscript. You can see it can get kind of complicated just writing out the math. But basically you can think of like, if you ever see these double summations, try to do basically this summation first, or whatever, inside or outside. You're supposed to do the inside one first. But I'm a physicist. I did physics, so like I never like to do this. I'll mix them around every time. But you should do the first one, the most inner one first, okay? Just know that sometimes technically, mathematically, you should do it. But a lot of times you can do the outs one first too. But anyway, this allows you to basically have any number of features with any degree of polynomial in there. So cool. And that means we can generalize it to something beyond a linear regression or a linear set or predictor. So I guess regression line. Okay. So real quick then. So we kind of look at these things. Like for example, if I drew that line in there, like I did before, that's not going to be very good. This clearly is much better. Okay. Okay. And then we also have this version right here too. So I kind of want to ask you guys, okay, so there isn't a limit on the degree of polynomial. So I already kind of said it's like, it could be computationally high, but there's not like a real reason why we couldn't do like, a degree of 5. There's not like a big reason. But let me ask, let's talk about like the advantages, disadvantages. So we have an R squared value, right? That's how we measure how good our model is on with our predictor. And so if we have a more, we call it more complicated, which, it looks more complicated. If we have a higher complicated model, are we able to achieve a higher or lower regression or R squared value? So really what I'm asking is which one has a better R squared value, this one or this one?
Maybe you're getting at, I'm just guessing, but overfitting in the second one?
That's what we're going to end up getting to. But going further, let me just ask you guys, what does R squared represent? If just in your own words, what is R squared? Like, if you were to explain it to like, a 10-year-old, like, what is R squared?
The difference between the predicted and actual squared.
Good, right? It's just the difference between the two, squared. Basically, it's just saying how good is our model predicting our data, right? Like how well does it fit? That's really what R squared is kind of trying to like summarize. So let me ask you, which one looks like a better R squared? Remember, higher R squared is better, right? Which one would be a better predictor of our data right now? Like what fits the data better?
The second one.
Second one, right? Yeah, this actually has a higher R squared value. And that makes sense because you can see the data points are, whenever it comes by the data points, they're pretty close. Compared to here, it's still kind of off on some of these parts, but you can kind of see it gets a little bump up here and even dips down just to kind of come in at this angle. So you actually can get a slightly better, maybe not even slightly, maybe a significantly better R squared value. And then kind of going even more simple, or like compared to more simple. The simplest one we could do, right, is our linear regression and doing our line. And clearly this is simple, this is more complicated. Clearly this one's more, not more accurate, but has a higher R squared value than this one, okay? And so in general, is that if we have more complicated models, higher degrees in your polynomial, we can get a better R squared value. But here's a real quick question. So I kind of mentioned a little bit polynomial degree. It's like, how many variables should we use? Like, what would be a good rule on that? And I'll leave that kind of open. I want you guys to say like an exact number, but it's kind of like, there's not like a real clear, like when do you use x to the power of 5 versus, x to the power of 2, right? Or, x to the power of 10. Okay? Like, Like, how do you know when to stop going? Like, could we have done like x to the power of 30? Yeah, we could have. And we get a better r squared value, right? So clearly I'm kind of leading into something here. It's like, why might this be complicated? And I think Paul kind of was on the right track of like what I'm leading into. But why wouldn't we want to make a very high degree polynomial, basically making it more too complicated? Like, what would be a disadvantage for that?
Any unaccounted for variables or anything that's slightly off would kind of amplify in magnitude, if that makes sense.
Yeah, I think you got the right track on there. I don't know if does anyone else want to add anything to that? Okay, yeah, I think that's a good way to kind of think about it. It's that there's any, like, if you look at this, clearly there's some kind of like general, like probably parabola, but like, data's, we have random noise, we have just, randomness in general. Is that you're never going to have, like, if your data ever looks like perfectly on the line, like you should immediately be suspicious, being like, how is that possible? Like, why is this perfectly, like on the formula? Like, if you can draw a perfect line through this data, right, very simply, you kind of be like, that must not be real data, or something weird has happened. So like whenever we kind of come across this, if you have a really complicated model, you can actually, like, these points are just all on top of each other, but if you imagine they're more spread out, you can actually create a model with a high enough polynomial that will perfectly go through each data point exactly as set. And we've kind of seen this before. That's not good, right? And I think we might have mentioned a little bit before something called overfitting. Paul just mentioned it, and I think Matt had mentioned it at some point. I actually don't remember if we actually talk about it formally in the curriculum. But the point is that we're making our model so complicated, it can fit the data perfectly. And why won't that be good if we can fit our own data perfectly? It sounds like a good thing, right? But why wouldn't it be a good thing?
Because new data is different.
New data is different, right? Yeah, good. Our data, we have a new data point, if this fits perfectly on it, and we have one data point that's slightly off from that point, like right here, but the model went something like this, it will completely miss that point. Basically not do a good prediction on that new data point, even though that parabola would actually make more sense. Okay.